Hello there, ladies and gentlemen. Here are our electrical current notes, and let's get learning. The first thing we're going to start talking about is how a battery works. Now, some basic things that we all know: a battery has a positive end and a negative end on it. And right here along this line, there is a barrier. Now, we all know that negative charges are attracted to positive charges, and positive charges likewise are attracted to negative charges. So these two opposite ends of the battery should be attracted to each other, yet they are separated, and that was designed on purpose by the people who created batteries. Batteries are very, very useful to us. I'm sure, as you know, we use them every single day. So why did they make batteries like this, to where one end is positively charged and the other end is negatively charged? Well, I'll tell you why. Because they had an idea in mind that they wanted to connect a wire to this battery on one end and the other, and have some sort of resistor, some reason to run this battery. And therefore, at this point, whenever we have a wire that is connecting one end of the battery to the other, the electrons that are on this side finally have the opportunity to get to this side. How do they do that? They go through this conductor on the wire. So they say, oh man, we can finally get to the other end of the battery. We can finally meet up with these positive charges that have been on the other side of this barrier for so long. And that is the design of a battery in a very quick nutshell. We'll keep coming back to this, but just kind of keep that in mind as we go through this slideshow. Alright, so let's start talking about electrical current and what electrical current is. So electrical current is just the flow of electrical charge, and that electrical charge is electrons. So just like a river has water flowing through it, electrical current has electrons flowing through it. And we need to understand that current flows when there's a potential difference between 2 points. And we call that potential difference voltage. Remember, voltage is the same as potential difference. So let's talk about our battery again. So we got our battery down here, and this is our positive end, this is our negative end. And what this battery has is a difference in charge. Difference. It has a difference in charge, and when the battery is just sitting there and there's no wire connected, it has potential to send electrons through, but it's not sending electrons through, but it has that potential to. So we have a potential difference. You see how that works out? So that's why we call voltage potential difference, because there's potential for the electrons to move, and the battery gives those electrons that potential. So, charges move until the entire conductor is at the same potential. So, remember our battery that we had, and there's a wire connected to it. And whenever those electrons are flowing through the battery, like this, like so, and the electrons flow through, at some point, there's going to be the same number of electrons on each end of the battery. That's when your battery is dead, and the battery has become neutrally charged all the way through. So charges move until there's the same potential everywhere. So that means there's the same amount of electrons everywhere, and everything is neutrally charged. That's when the charges stop flowing, and that's when your battery is dead. Alright, so you must have some sort of charge, or what you could call it like a pump, like when you're pumping air or something. So some sort of movement to maintain a potential difference. So there needs to be some sort of charge on the battery to keep that potential difference so that the battery can maintain its voltage. And we measure electrical current in amperes, shortened amps, represented with the letter A. So, there are two types of electrical current we need to be familiar with. The first type is DC current, also known as direct current. This was created by Thomas Edison. This is when current moves in one direction only, and this is when we use batteries. So batteries use DC current. Very important, the electrons move in one direction and one direction only. Then there's also AC current, alternating current. This was created by Nikola Tesla around the same time that Thomas Edison made DC current. This is when the current moves in one direction and then in the opposite direction. So on AC current, the electrons move one way, and then they get pushed and move the other way, and they just kind of go back and forth and back and forth and back and forth. Instead of the electrons just going one way, they're kind of like going forward, then backwards, forward, backwards, forward, backwards. All right, so in AC current, energy can be transferred over great distances. With DC current, there would have had to been like coal factories about every mile to power a city. But in our houses, we use alternating current because alternating current can be transferred over large distances. So AC current is very, very good over large distances. And so we got the power company miles and miles away from your house, but that electricity can still get to you because they're just pumping the electrons back and forth and just making them go back and forth instead of sending the electrons all the way to your house. All right, so let's talk about a voltage source. So a voltage source is just anything that gives you that potential difference to maintain a steady current flow. So that's the whole thing with electricity. You want to have the current steadily flowing through. You can also call your voltage source a charge pump if you choose to. In your house, you have 120 volts coming out of your outlets in your house, except if you have your dryer, which usually is about 240, I believe. So 120 volts can be very dangerous. Suggest you not playing with it. So voltage is what causes current. Voltage is what gets the electrons moving and gives the electrons their push so that they can move through the circuits. All right, so let's talk about charge pumps and the three types that there are. So the first type is generators. These are things that use mechanical energy or some sort of kinetic energy where you're doing work and it turns it into electrical energy. For example, windmills, hydroelectric dams, and hand cranks, and coal plants. So all these things take mechanical energy and they can turn them into electrical energy if we so choose to do that. Then there's also photocells. These are things that take light and turn it into electricity. And if you're thinking, oh, that sounds like a solar panel, that's correct. And your calculators in the classroom generally have the little tiny solar panels on them, and those are photocells, and they convert that light from the lights into energy, electrical energy. And then we also just have our normal batteries, like what I was talking about earlier. They have chemicals inside of them, and those chemicals are converted into electricity. All right, so let's talk about batteries. There's three types of batteries that we use. There's the primary types of batteries. These are like your Duracell, your Energizer, just anything that you plop two AA batteries in, or a D-cell battery, or a 9-volt battery in. And after they're done, you throw them away. And then there's also the secondary type of batteries. These are batteries that are rechargeable. There is an ability to take the electrons that have moved from one end of the battery to the other, and that you can take those electrons and put them back where they were originally, such car batteries. Car batteries are always being charged as you're driving them. So that's what your alternator does. Your alternator is what charges your battery, so it takes that mechanical energy that you're creating while driving, and it's helping charge the battery again. And there's also the fuel cell type batteries. These are ones that continually pump fuel in or chemical into a battery, and it's constantly using up those chemicals. For instance, the space shuttle uses oxygen and hydrogen, and it produces electricity and water. So very interesting use of a fuel cell that has been used on spaceships. All right, so let's talk about electric circuits now. Now, electric circuits are what we actually create to use the electricity. A definition is just a closed loop through which electric charges can flow through. So there's got to be a closed loop. So three conditions that electric circuit must have for it to work. And if it does not have one of these three, the electric circuit will never work. First thing, the circuit must be closed. That means that there must not be any sort of disconnected wire anywhere. So, for example, if I draw our battery down here, and I have the wire here, and I have some sort of resistor, and I have the wire here, well, the circuit's not closed, so the electrons are not going to flow through. The circuit has to be closed for any sort of electron flow to happen. So let's look here. Let's try to close the circuit. So there we go. It looks like the circuit's closed now, although it looks ugly. But the circuit's still closed, so now electrons can flow through it once again. So that's the first criteria that you must follow for circuits to work. The second thing that the circuit must have is a potential difference. So the power source that is put into the circuit must have more electrons on one side than the other. That way the electrons will want to flow through. So there must be some sort of potential difference in the circuit. And the last but not least, there must be some sort of voltage source, such as a power plant or a battery or something like that, that can create a pump or some sort of charge movement in the circuit. And energy flows through circuits to cause a vibration of electrons in appliances in your houses and things like that. So whenever you are paying the electric company, you're not actually paying for electrons to flow into your house. What you're paying for is the energy that is produced at the power plant to pump your electrons, because remember, your houses are just using AC current, so there's not any new electrons being pumped in. It's just using the existing electrons in the wires and moving them back and forth. And that is what is causing your TV, your lights to turn on, things like that. So the electric company is just creating energy and pumping electrons back and forth, and those electrons are pumping back and forth in your appliances in your house. So let's look at a circuit diagram, what we have here. These are also called schematics, if you want to use a technical term. These are just a way to represent all the electrical devices that we're going to be using. So for instance, right here at the bottom, there's a switch, and you can see that the switch is open. And if the switch was closed, it would look like that, and then we would have our complete circuit. But right now the switch is not closed, the switch is open, so there will be no flow of electrons. You got your ammeter here. This is measuring this is measuring the current going through the wires. So an ammeter is what we use to measure current. Right here is your resistor. Any type of resistors, anything you use electricity is a resistor. And this is your battery, this is your voltage, this is your power source. So this is sort of a general idea of what a schematic looks like. And here's some more symbols that you can look at. We got a voltmeter down here on the bottom right. We got battery on the left. We got a cell above it. All sorts of different types of symbols that we can use while we are drawing schematics. Alright, so now we have to talk about electrical resistance. The whole reason that we have electricity flowing through wires is so that we could plug something into it. And everything that we plug in is a resistor, and it causes resistance in those electrons. And that resistance of the electrons is what causes things to light up, to illuminate, to work the way that we want them to. The definition of electrical resistance is resistance that a conductor has to the flow of charge. So there's some sort of like slowing down of the electrons as they're trying to move in this general area. And though that slowing down causes, like, I guess you could say, friction between the electrons, and that's what causes some sort of illumination that we have grown to depend on so much. And resistance. There's all sorts of things that resistance depends on that can adjust the resistance of different things. So for instance, the material. So is it a really good conductor? Is it a really bad conductor? That can affect the resistance of electrons as they're trying to flow. Another thing that affects resistance is the thickness of the wire. So the thicker the wire, the less resistance. So if you have a very, very thin wire, there's usually a lot more resistance in a very thin wire than a very thick wire. Because if you think about it, if you have a very thick wire, then the electrons can flow easier. But if you have a very thin wire, then the electrons are kind of crammed in together and they can't move as well. So a bigger wire, a thicker wire gives less resistance. Another thing is the length of the wire. So however long the wire is, it could cause more resistance, because if you think about it, the longer the wire, the electrons are trying to flow through this wire, and they keep bumping into different things along the way. So the longer the wire, the more resistance, and it kind of can slow down the flow of electrons as they're trying to move. Temperature is also a factor in resistance. So the lower the temperature, the less resistance that we have. So actually, electrical things tend to work better in some cases if things are cold. It just allows the electrons to flow better because there's less resistance. And resistance is measured in ohms, and that funny little O looking thing is omega. So start practicing drawing that so that you can write it as your units whenever you're solving problems. And that leaves us up to Ohm's law. Ohm's law is stated technically, current is directly proportional to the voltage while it is inversely proportional to the resistance. Basically what that means is voltage equals current times resistance. That's Ohm's law right there. Ohm's law is very important. We're going to use this a whole lot this semester, so be prepared to see this a lot. The V stands for voltage, measured in volts, represented with the letter V. That's one thing in physics that finally makes sense, right? The V is voltage measured with V. We represent it with the letter V. How about that? Everything lines up nice and perfectly, and then things fall apart again. Current is measured, represented with the letter I, and the units are amps, the letter A. Just got to remember that pretty much. Current I, units A for amps. And R stands for resistance measured in ohms, which is that omega O. Also, high voltage means high current. That's what this equation is saying. The voltage is directly proportional to the current. So if voltage goes up, current goes up. Also with resistance, if you have a high resistance, that means you have a low current. So if resistance gets bigger, if voltage stays the same, that means the current has to go down. It also just makes sense because if you have a high resistance, it's slowing down the flow of electrons, and that means a low current. That means that the current isn't flowing as fast, the current of electrons. And we got all these different types of resistors, devices found in electric circuits that regulate current in a circuit by providing a specific resistance. So sometimes the things you plug into the wall have too much current, and there are resistors placed inside of your electronics that slow down those electrons before it actually gets into the electrical circuits, and it can end up harming different parts of your electronics if you don't have those resistors in there. And usually they're put in by the factory long before you get them. And then we have our electric power. Electric power is what it says here, a rate at which electrical energy is converted into another form of energy such as mechanical heat or light. So what is the rate at which different forms of energy are being transferred into electrical energy? So we got mechanical energy when you're like pumping a hand crank, and then that hand crank is turning on a light bulb. So that's mechanical energy into electrical energy. So electrical power is how fast, how quickly are we turning the other form of energy into electrical energy. And there's a nice equation that you can use to work it. Don't get too worried because this equation is pretty much very simple. The main part of it that you'll work with is power is equal to current times voltage. So make sure you're familiar with that. But also, power is also equal to, let's mark this out, and this, power is also equal to voltage squared times resistance. So that's just another way that you could work out these problems. If you're given voltage and resistance, you can still find the power. All right? And same thing goes over here at the very end. So we have power is also equal to the current squared times resistance. So in your problems, when you're solving them, if you're just given current and you're just given resistance, you could use current squared times resistance. And all these are on your equation sheets in class. You don't have to worry about memorizing it, but it's good to have it in your notes. So make sure you have that written down, and we will be good. Remember, power, P, is measured in watts, W. So power is always measured in watts. V is voltage again, and I is current again, once again measured in amps. All right, so the electric power companies, how do they know what to charge you? Well, they charge you by what's called kilowatt hours. So a kilowatt is 1,000 watts. So you got to remember, kilo means 1,000, and if you have 1 kilowatt, that means you have 1,000 watts. And what they do is they measure the kilowatts that you use every single hour. So the kilowatt is the measure of power, so you need to figure out how much power a certain thing is used, and then you need to figure out how long it's used, if it's used for 10 hours, if it's used for 10 or 15 hours, if it's used for 1 hour, how many hours was it used. So the equation to find the electrical power that is being used in a certain rate of time is E equals P times T. What that is, the E is the energy in joules, so E, energy in joules, or kilowatt hours. Joules and kilowatt hours are going to be very similar. Power is measured in watts, and T is measured in seconds. But instead, for this particular time, we will be measuring power in kilowatts, and the time will be measured in hours, because the electrical companies charge you due to your kilowatt hours that you are using. Okay? So keep that in mind. But if you're just going to calculate pure energy, you need to use these units right here. Whoops, let's go the other way. So if you're going to take the cost of how much you're going to try to calculate how much it costs to run a light bulb or run a TV, you need to take the kilowatt hours, so you figure out the power, the kilowatts, and then you multiply that by the number of hours that it was used. And let's say that they charge you 10 cents per kilowatt hour. Then you'll take the kilowatt hours that you had, multiply it by 10 cents, and you'll get your number. If you want to go look at a power bill, they always have the rate at which they charge you for your kilowatt hours. A lot of times it's anywhere between 6 cents and 10 cents, maybe sometimes up to 12 cents. Just depends on the power company. How much are they going to charge you for your kilowatt hours? I suggest you go try to find a power bill somewhere and see how many kilowatt hours you're being charged at your house. Sometimes it's very interesting to look at that. All right, so let's talk about electric shock, something that's always very interesting to people. If you have dry skin, that usually means that your body's resistance to electrical flow is about 500,000 ohms. So you usually have a lot of resistance in your body. So your body can resist a lot of electrical flow. But if you're wet, like you just jumped in the pool, your resistance drops to about 100 ohms. So that's a big, big difference. So if you have dry skin, 500,000 ohms resistance. If your skin is wet, your resistance drops to 100 ohms, and that's because you have water on you, and that water is usually a better conductor than just your bare skin and bare body. So there you go. And interesting thing about birds sitting on power lines. The birds, when they sit on the power lines, they don't get shocked, they don't die, unless they touch something else or unless they somehow end up being grounded. That's because they have the same potential difference through them. That means they got the same amount of electrons flowing through them as what's flowing through the wire, and so there's no shock going on. But if they were to touch something else that didn't have that same amount of voltage in it, then they would get shocked, such as if they were to touch the power pole instead of the power line. If they had 1 foot on the power pole, 1 foot on the power line, then they're creating a huge potential difference in their feet, and that would cause a gigantic electric shock to go through them, and they will be cooked and fried in a second. And a little more about electrical shock. So whenever you look at things that are plugged into the wall, if it has a third prong, that third round, more circular prongs at the bottom, that is the grounding line in your electrical appliances. That takes the excess electrical charge and puts those charges into the ground so that those excess electrical charges do not build up in your appliances, which could cause a problem. So that's what that grounding wire, that third prong is, that's your grounding wire, and it gets rid of your excess electrical charges. And whenever you do experience an electric shock, it overheats the tissues in your body, and it disrupts your normal nerve function. So your nerves, your body can kind of tighten up whenever you get shocked, and that's why whenever someone gets shocked, it's very hard for them to let go of the wire, because their nerves just cause their muscles to contract, and they don't have control over those muscles anymore. So if you ever see someone who is actually being shocked, you do not need to go grab them and pull them off, because you will become shocked too. Your muscles will contract, and you'll just hold on to them tighter, and you'll both be getting electrocuted at the same time. So what do you do if you see someone getting shocked electrically? You need to get rid of them, like push them away from it, using some sort of insulator, like a wooden stick. If you happen to have maybe something gigantic and rubber, use that. But whatever you do, don't just go up and grab them, because you're going to be in the same situation as them. You need to find some sort of insulator and knock them away, knock them onto the ground, away from that wire the best you can, so that you are not harmed also. So how much damage does electrical current do on the human body? How much electrical current needs to go through you for you to actually get hurt? So if you have 1 milliamp of current flowing through you, you can barely feel that. If you have 5 milliamps, you'll start to feel a little bit of a tingle. 10 milliamps, your muscles start to contract. That's when things start getting dangerous. 15 milliamps, you start to get a loss of muscle control to where you can't even fight it. Your muscles are just doing what they're doing with those electrons going through you. 50 milliamps, that is to where you could possibly be killed. And 100 milliamps, that will always kill you. And keep in mind, 100 milliamps is only 0.1 amps. Very interesting. And current is what does the damage. The flow of electrons is what causes problems in you. If you have if you're going to be electrically shocked, and you got to remember that the current depends on the voltage and the resistance. So what type of resistance does your body have at the time, and how much voltage is going into you? And last but not least, safety devices that we put into electrical circuits, and certain just safety precautions that you need to remember when you're working with electrical appliances. One byproduct of current flowing through wires, so when current is flowing through wires, especially at a very high rate, it can cause a lot of heat. So you need to be careful sometimes if you're using a lot of voltage, or something with very low resistance. If the electrons are flowing through very fast, you're going to experience some heat, so be aware of that. Too much electrons flowing through a circuit can actually start a fire. So that heat can get to the point to where fires, sparks, and everything's fly. So also you need to keep that in mind as well. And there's two safety devices that we put into electrical circuits so that, if we're away and some sort of electrical issue happens, there will be some sort of safety device in there to cause things to not go so bad. One of those things is a fuse. A fuse is something that whenever too many electrons flow through, the metal in the fuse will melt, causing the circuit to open up, and that will stop the electrons to flow. Because remember, you need a closed circuit for electrons to flow, but if the circuit is opened, then the electrons will stop flowing. And also we have circuit breakers. These are in your house. They work like fuses, but instead of melting, what they do is they trip, or it's like a switch and it turns off. So if there's too many electrons flowing through, the breaker will trip and it'll turn off, and it'll stop the flow of electrons before any damage can happen, or any serious damage can happen. So those are two things that we put into electrical devices that can help us keep electrical devices safe. Thanks for watching.